Okay, hello everyone. Hope you're all having a great morning so far. I am excited to welcome you to the latest installment of our AI webinar series. So there's no question that generative AI has been the hottest trend for the last year and a half, and today's session will be focused on what's next in on-device generative AI. I'd like to welcome Joseph Soriaga, who is the Senior Director at our Qualcomm AI Research Group. He is excited to present on this topic. So please type in your questions in the chat and we will address them at the end. So Joseph, take it away.
Great. Thank you. Thank you very much for the introduction, and thank you all for tuning in, spending your morning with us today. I'd like to, for today, my goal is to, my goal today is to give you a sampling of many of the things happening in generative AI, and also what we're doing at Qualcomm AI research and across Qualcomm AI commercialization, to give you a sense of the things that are happening, the trends that are going on, and how are the efficiency techniques that we're working on evolving to intercept these trends. We will also talk about adaptation and personalization. This is a unique and key advantage for moving to the edge. And also, we'll go into thinking about agents and embodied AI. This is, the next exciting phase, and really another good aspect for edge because of the situated real-time interaction that can be possible. So, without a doubt, multimodality has been the big push recently. And it started really with transformers, not just going into generative AI, but even at the transformer level, a lot of modalities have been harnessed and, if I could say, fused together because of the ability of this model architecture. We've seen this in our contributions in the past year on, say, multi-camera and LiDAR in the space of automotive, aligning that for bird's eye view. Even in the space of wireless and looking at different aspects of controlling the system, like beam management. How can we put in modalities across positioning and camera and RF measurements? And then going a step further, a research team was able to look at a different type of geometric algebra for the way the transformers are architected, which fits very well the physics behind robotics, and provides some advantages there with training and efficiency. Now, with that in mind, it's natural to see how does this extend towards generative AI. And you're seeing a lot of this already in commercial offerings across the industry, open source offerings, just different demonstrations of capabilities throughout this year and even late last year. Voice UI is, of course, a natural place, which was exploited a lot last year. Being able to do language is very natural, that we also just want to interact by speaking. Now, multimodal models where they can see, maybe deal more directly with audio instead of just transcribed speech, and take in other sensory inputs is a next exciting phase for this. And then in terms of generating content, the idea of having not just images, but video, 3D, things that are richer and help us to have even more immersive experiences through this generative AI is the next big step. When we look at what are the capabilities and the KPIs behind this, you can think of in just the context lengths themselves for the models, the LLMs, they're going to grow a lot bigger, because now you have to be able to address an image, address different modalities that have maybe different ways of tokenizing, and then also just the interaction with databases like retrieval will warrant the need for larger context, so that all of that can be processed in LLM. Being able to fine-tune the models is very important for different domains, even user-specific cases. And then moving to higher resolution is important for the generative, let's say like image, video, and 3D. Especially as we start going into these other modalities like 3D, it's going to be important to have a high resolution to be able to have that experience of moving things around and putting them close to you or farther from you. So these capabilities are certainly growing. These KPIs are certainly broadening, and we'll talk about how we're intercepting that with a lot of the innovations that we're doing. Edge continues to also be an important focus because it's a great complement to what's happening out there. A lot of amazing innovation is coming from the cloud, of course. The models are almost without bound in terms of the sizes and the amount of training they can put behind them and so forth. And so that aspect always is always there to pioneer what's the latest capability. But at the same time, the idea of like spreading this out, having this closer to the user, reducing latency, taking advantage of privacy, personalization, having things more ubiquitous, and even lower power. That's the great complement that being able to have things on the edge is. And then once we have these two, it's natural to build a hybrid AI workflow around this. So now let me get to a sampling of some of the techniques. And just to give you a kind of an outline of some of the things we'll talk about today that you've seen before also. Distillation, quantization and compression, speculative decoding. These are techniques that we introduced last year in our previous webinars to give you a sense of the different tools that we can use to really make running these large models for generative AI efficient on the edge. And each of them can be done to address different aspects of the efficiency on target. What's great is that the things that we innovated through the course of last year continue to be good foundations for going forward. And then we're looking, new things I'll talk about this year are also when we look at, say, video, and also talk a little bit about heterogeneous computing. So generative AI, because of the size of the models, it is natural to immediately focus on quantizing them, trying to keep the number of parameters large as possible, but then having that representation memory footprint be as small as possible without losing any of the accuracy or very little of it, and the capability of the model. There has been a lot of progress in moving to 4-bit, and that's helped to reduce that footprint fourfold. And it helps to essentially reduce many things around it. There's the memory storage, there's the bandwidth exchange between the chip and the memory. There's improved latency, there's improved power, the benefits across the board for that. And then there's the challenges implicit with this. There's the accuracy that we have to maintain. And then there's a trade-off of how much effort are you going to spend in quantizing the model versus how quickly do you need to, or how much accuracy or performance are you willing to give up. So with this, core tool, actually this is a tool that's applicable not just in quantization, but a core tool that we've talked about is knowledge distillation, where we can start with the large teacher model, which in the case of generative could be the original language model or language vision model. And then we can use that to generate soft labels to go and fine tune a student model. And then this aspect of fine tuning helps to focus on certain things that we need the student model to do, but then the student model can be suitably more efficient for the target device that we're deploying. And interestingly enough, as we'll talk about, there are different ways to think about how a student model might be more efficient. It can be not necessarily smaller, but it can be the same size, but it tries to execute things in less number of iterations, or it might actually be smaller because of quantization, or it might be smaller just because of its overall architecture and parameter size. So there are different ways that we leverage this. Now, with that in mind, last year, we went into the idea of using distillation to do quantization-aware training. And we did this specifically for LLMs. Part of this was because the training pipeline for LLMs is quite sophisticated, because there's a pre-training on a corpus, there's instruction fine-tuning, there's even reinforcement with human feedback. And these aspects, you don't necessarily want to run through and do quantization-aware fine-tuning just with that entire process. And so distillation was a way to take into the quantization fine-tuning process all of these implicit capabilities that were learned through that complicated training procedure, and still be able to address the perplexity, the accuracy, other aspects related to the models that were focused on, like chat, also had certain safety and toxicity emphasis last year. And that's important for us to make sure that we maintain that. Altogether, still being able to go after really aggressive quantization targets like 4x smaller. Now, this allows it to be significantly less complex than training, but it's still somewhat intensive technique for quantization-aware training with knowledge distillation. And later last year, the team, some colleagues in AI research published a paper looking at what is the reason that we need to do this fine-tuning? Where are the challenges in the quantization, dynamic ranges, and so forth that arise in LLMs and transformer models, and then what can we do about it? And interestingly, some of the core problems they pointed out are when the models come out trained, we see sometimes these residual sums where we have a very large distribution and a very tight distribution being summed together. And this is where a challenge arises in quantization, because we cannot necessarily, with a uniform grid, pick out both of them with good accuracy. Now, interestingly, instead of, say, fine-tuning the model to be able to keep these distributions more closer together, what the team found is that the way that attention is architected can arise, can give way to these large dynamic ranges in distribution. And it comes down to, is this nice phrase, helping these attention heads do nothing. Because once in a while, you have to look at this attention window, and it's important not to be able to attend to anything. But because of the way the transformer is architected, it has to put attention to something. And that through the course of the training process, starts to learn these no-ops that drive these dynamic ranges, in short. So the team said, what can we do about this? Can we influence maybe the pre-training of these models such that they don't have such large dynamic ranges? And in the result, if you can reduce those dynamic ranges, maybe you can have much easier ways to quantize the models. And so there were two approaches that they proposed, and I'll just kind of mention them in short here. Like there's a clipped softmax, and then there's a gated attention. And basically, by introducing these, what they're able to show and looking, this is a table of results for 3 different models. 2 are language-based, BERT and OPT, encoder, decoder, and then just a decoder-only model. And then we also had a vision transformer. And basically, if we look at how the model pre-trains with these solutions, it can maintain the accuracy at the high precision, which is good. That means that the pre-training itself is just as good as before. It doesn't discourage anyone from putting this into their pre-training flow. But then if I go look at this last column, when we do very simple quantization techniques, the resulting ranges in those activations, like that residual sum that I showed previously, are much better for quantization. And now we have a closer alignment with the target perplexity of the original model, or the target accuracy of the original model, 32-bit. So the idea here is that if people go and pre-train in a certain way, then it makes the idea of quantization later much, much easier. And that can help the overall turnaround in the deployment. Now, another important innovation has been not just in making the flow easier and looking at post-training quantization, but also can we go lower in the quantization, the bit precision. And vector quantization is a well-known technique. Here we're looking at applying it for the code book of quantization for the weights. And so the idea here is that instead of a uniform quantization grid, we can start thinking about a quantization grid or distribution of points that is better matched to the distribution of the weights. And so by doing this, we can be able to maybe get a better 4-bit representation, or more importantly, get below 4-bit and continue to reduce that DRAM footprint, or that bandwidth exchange between the chip and the processing unit. And which you can read about more on arXiv. We show essentially both the footprint can go down, and then as we go to a relative 3-bit or 2.25 bit per weight. And the footprint can go down in terms of how many bits overall are being used to present the model. And also the latency through, we had a prototype implementation on CPU, just to show that you can also encode and decode fast enough with this additional overhead of decoding and encoding this quantization grid, and still see a latency benefit because of that bandwidth exchange is reduced. So that is the kind of the promise of the technique. And so what's left is, can we get this technique to have a good accuracy? And in short, the team was able to perform a good amount of experiments on applying these to common models like Llama 2, Mistral 7 billion, and even the Mixtral MOE model. And looking at the progression of, say, 1 dimension to 2 dimension to 4 dimension, they're able to have good perplexity and good average accuracy scores that beat the state of the art when going down to these low bit widths. And moreover, this is a post-training technique. So instead of relying on knowledge distillation and quantization web fine tuning, the team was able to look at the model weights and also some representative data that the model will work on in order to be able to get to these lower bits per wave representations. So that's essentially some of the ideas that are coming forward to help us reduce these model sizes in the space of quantization. Now I'll switch gears a little bit into this technique that we talked about a lot last year on speculative decoding. So here, now the idea was that instead of having the large target model generate each token, what we can do is have a much smaller model generate draft tokens, and then the large model can process a batch of tokens and then correct them. And if it ends up accepting a majority or even more than half of the draft tokens, there's essentially a bandwidth savings in that the large model is called and generates more than one token whenever it's called. And so that has been, a very strong way to get beyond the bandwidth limit that might be on edge devices, or be able to reduce the bandwidth utilization and trade that off for power, or just reduce the activity on the DDR for other applications. So the natural question is, what happens when we go into multimodal? And what is interesting is that the team was able to look at an example model, Lava, where that is essentially shown in gray, where we have a large language model. This essentially from Lava, from our perspective, is frozen, and it has its own vision head and an adapter or connector to help translate these into embeddings that can be processed by the language model. And they're aligned with the representations that the language model is doing, also for text. And then the text tokenizer would put its text so that we have our vision tokens and embeddings, and we have our questions from the prompt in the text, and then we have our answers that get generated. Now, if we want to incorporate speculative decoding, we can introduce a Lava drafter, so to speak. So much like the chat drafter that we had in a previous proof of concept, now we can take that, it's already pre-trained just to do text, and we can introduce the idea of a projector for the draft. And together with everything else frozen, we can fine-tune this to align with the target, and then through a similar distillation, try to get a high acceptance rate from the target, from the draft into the target. So interestingly enough, a lot of what we have invested in for training a draft for the speculation of the large language model can translate over to this multimodal. And then the idea in general of speculating for multimodal allows us to continue this innovation as this trend continues. Some experimental results are shown that we can essentially, last year we were looking at speculative decoding just in the domain of text. We played around with our team played around with doing this, and they were able to see similar, let's say, estimated speed ups of the token rate because of that bandwidth decrease that happens from the draft having a lot of tokens accepted. So this allows us for another promising extension of what we're doing towards speculation. And speculation, again, is this idea that allows us to trade off compute for less bandwidth usage, which tends to be the bottleneck in these applications. At the same time, I should just also mention that earlier this year, we showed the first large multimodal model on a phone, and this essentially has the essentially allows us to incorporate this same 7 billion parameter LLM, but now with that vision head, and now we can answer and we can ask multi-round dialogue questions with the image that we've taken. And it's an amazing starting point that many open kind of like open set type of questions you could ask with these images. And there's interesting reasoning that is demonstrated from these. It's a good starting point for further applications. Now, that essentially constitutes a lot of the things happening in the large language model domain. Now, let me come back to the large vision model space. And just to remind folks where we were at, we did look at diffusion as a core component. This continues to be very key in generating images, moving to higher resolutions. And in this, the idea of introducing basically UNet to denoise images into to denoise these latent representations into images is still the key bottleneck that we're after. And there are further innovations in this space the team has been doing to help to make this more efficient in the space of image, and then also lead it towards effective video. So one interesting aspect about looking at this diffusion for images is that we are running a UNet at different resolutions. And there's low resolution features, and then there's high resolution as at the extremes of this. And then if we look at how much these change with perturbations, we can see that, well, the high resolution features are very sensitive, but then the low resolution features, they can withstand some level of perturbation and still maintain essentially that consistent semantic context with the image that's generated. And so from that observation, where the low resolution features can be perturbed, suggests that they're robust, and maybe we can take advantage of some efficient architectures in that part of the UNet. So this idea of clockwork architecture was come up from the research team, where at the low in the diffusion process, if I go from each iteration, there's a low resolution block that we were using for this denoising step. And now that we know that it's robust to perturbation, we can consider looking at some adapter that might be simpler to implement. It may have less attention operations, for instance, or it might even just do a simple copy, depending on how many steps overall that we're running the network. And so, and this adapter furthermore can be optimized through distillation against the original UNet for the target, the application of how many steps or what overall architecture we're starting with. And interestingly enough, this observation and this solution helps us to get a further reduction in the flops, on top of the things that we were doing last year to go and distill the stable diffusion model down to run in less than a second. So this is another great technique that is continues to help us extend the space of image, run image faster, run at a larger resolution, and that helps us to think about bridging the gap into video. But video has its own separate challenges. Temporal consistency is an important one. Generating images through denoising, because it's a diffusion process, there might actually not be very good temporal consistency between images. And so it's important that when we harness this technique, we have some way of tying that in better. And then video naturally, because we may be processing multiple frames, there's a high computational cost associated with this. some ways that video is being addressed are, as with this example model from Meta, as a Fairy. This is a video-to-video generative AI model that allows us to, say, stylize a particular video. And in short, there are two key aspects of this. There's extracting states from anchor frames in the original video, and then we go and we edit the video across the remaining frames. And you can see a lot of the similar blocks that we had in the earlier Stable Diffusion diagram that I showed, where we have an image encoder, a text encoder, and also a UNet where there are diffusion steps involved. And when we look at this towards running on device, that's where we want to look at, are there optimizations that we can do cross-frame to help get the memory down, to help get the runtime and then compute more efficiently done. A lot of the optimizations that we're doing on the UNet itself can, in the case of Stable Diffusion image generation, they now allow us to carry that over because this is, again, a core block within this. And so when we start editing the remaining video frames, those optimizations that we did in the UNet can help us to carry this processing of the video be much faster. Because ideally, we want to have some kind of an experience where the video on the phone can be stylized in a reasonable amount of time, that it can be interactive with the user. And then, as we had done in the previous cases, there might also be further optimizations we can do to reduce the batching that might be related to guidance conditioning. This is, the team is continuing to progress. They were able to make large reductions in computation and memory that help us to get it positioned more towards running on device. And it's a good path that we're on, and we hope to have more on this later in the year to share with you. But you can see how interestingly we're able to take the original video and then stylize it in these different ways through those techniques that we showed in the previous slide. And also because we're investing in making a lot of these blocks more efficient, they carry over to this use case very nicely. Now, in coming to multimodal, as a general trend that's picking up a lot this recent year, it's good to reflect back on the different processors that are available when we look at an SoC. There are going to be use cases where we really have a low latency constraint. There are going to be use cases where we're going to have heavy image processing, which you can equate to lots of processing and compute, because there's compute per pixel that we're dealing with. And then you're going to also look at what's the best place to have sustained usage? So we're having model be pervasive or just always running and continuously. And so as a case study, if we look back at this AI assistant that we demonstrated last year, there are several components to this. There's being able to speak to the model through this automatic speech recognition block. This because of the constant continuous speaking that we need to have for voice UIs, we can put this on a low power part of the SoC. And here it's particularly the sensing hub. Meanwhile, the very large LLM and the processing involved for that, we can put on the NPU that's dedicated for accelerating larger generative AI models. And then we can take open source speech generation, this text to speech, to complement the process, so that whenever we can speak to the model itself can also speak back to us. And this, in particular, the way that some open open source speech models are run, they can be suitably run on the CPU without too much, with good efficiency, and also tie in with the latency that we need for responses. And altogether, we also tie in being able to interact with APIs. So there's a web API that we have with Skyscanner that allows us to have the LLM also prepare queries that can go into that web service. Now it's pretty amazing to see what the evolution has been for the processors, and in particular, we can zoom in at how the NPU has evolved. Many years ago, we were looking at audio and speech and moving a lot of that from hybrid signal processing to really end-to-end deep learning, and that has been a very foundational and transformative evolution. And then naturally, the next place has been looking at video, at camera, and in continuing to evolve speech. Now, this last year is when we took this pivot into generative AI at an extreme level, and then we can see that transformer support becomes like a very important aspect of the NPU. And then being able to address larger models also becomes an important aspect. And then looking forward, putting this all together for multimodal AI is the next exciting challenge ahead of us, which we've been talking about so far. And luckily, it leverages a lot of what we've invested in prior. It's a good reminder to come back to also the notion of what kind of model sizes we're looking forward to in the future. We have this landscape that is a couple of years old now in terms of looking at the space of models that were addressing different use cases academically. And we're watching how this continues to evolve and transfer into more of the commercial or proof of concept applications. And it's been pretty exciting to see how this can intercept a lot of the platforms that we're looking at. One important innovation this year, though, has been that Qualcomm has released this AI hub that allows developers to come and set up an account, look at the models, bring models, pick a target like a mobile chipset or a compute chipset or IoT chipset, and also look at a runtime like TensorFlow or PyTorch or Onyx, and then come back and be able to put these together and test and validate in the cloud and understand how these models might run on their device, ultimately helping developers understand how to deploy a lot of these innovations down from the perception stack up to generative AI on Qualcomm stack. So that's a great evolution that will allows us to consider bringing in these new things in multimodal. In addition to foundational model, important aspect to using these models is how can you change them for different domains. It could be domains of the application, or they could be personalization for the users. It is a challenge because of the model sizes to go and do a traditional fine-tuning of the model, because if there are, say, 7 billion parameters, we don't necessarily want to update all 7 billion of those parameters. And LoRa, or low-rank adaptation, has been one example of a very successful one to show how to have a much smaller parameter set, say, in the percent or even less than percent of the overall number of parameters, be updated so that we can update the weights in the model and the operation of the model itself. And this allows us to leverage a number of things. The fine-tuning of the model can be lighter. The implicit pre-trained capabilities, the original model, we can be more confident that they're not being forgotten in the fine-tuning process. And we can think about mixing and matching different adapters and bringing these together. So what was demonstrated along these lines earlier this year is that we can also bring this to device. And what was exciting to see is that we took the stable diffusion that we've been running, and then we showed how, as you can see in this demonstration, different adapters could be improved so that different adapters could be improved so that could be applied, and then we could show how certain domains in the generation process we can switch between them. And also all of this is being chosen on device, so that allows us to demonstrate the scalability of having different domains changed depending on the applications that need to be done, while the foundational model itself remains common and basically helps to reduce the the amount of memory that we're putting, or the amount of storage that we're putting behind having all these different use cases supported on the application. So this is an exciting step forward in allowing personalization, as well as just the broadening of applications that we can leverage for these. Now, the other important aspect of the models themselves and the adaptation of the models, how we're running the models, is the system that we put around the model. And so for LLMs, it's very natural to think about having an assistant built around this LLM. And to do so, there are certain aspects of the operation of having a voice interaction broken down into executing certain things that an assistant would need to execute. So what we show here is when we had a demonstration on this travel planning, different blocks are implemented where this text-to-speech initially would be, or sorry, the other way, this speech-to-text would be used to look at what kind of task needs to be run first. And then once that's classified, we can understand what the LLM should be doing with that task, with that query. And should that query be generating a response, or should that query be formulated into a response that goes to the web service through this Travel Planner API? This idea of orchestration helps us to guide that LLM to be able to do, to robustly and accurately do these tasks in the interaction with a person. Now, we took this a step further at the beginning of this year when we went to CES and showed how we could further enhance this in the digital cockpit. So having an AI assistant voice-driven in the car is even more so compelling, because unlike a phone, you don't necessarily want to be touching the screen or tapping or looking even at the screen. You'd probably be much more voice-driven in the car. And we demonstrated various things around that, not only doing a web API, but can we do control of different commands within the car? Can we also have a database for looking at the manual, asking questions about the car? And all of this, again, going through the text, speech to text, requires understanding of what task needs to be processed. And then once the task is understood, how should we process that task? And that is that relies upon the orchestrator interacting, deciding how the prompts should be formulated into the core LLM driving this. and then how to formulate these answers back to the user or into the different APIs that drive the application. So it is you see a lot of these applications in other places emerging. It is a great way that a lot of the abilities that we're instilling into the LLMs, especially as we're starting to go to multimodal, can be harnessed into advancing the state of interaction in our devices, everyday devices. Now, this is, of course, a point of time in progress. We are excited about what can happen beyond that. Maybe this is not ready for what you might be seeing in commercial products, but certainly it is very much on the like the natural evolution of what happens at the edge. The idea that we have models that are situated, vision, language, in the understanding what's happening around us, and then dynamically and in real time responding to these. This is very different than what I showed previously, because what I showed previously is it's turn by turn. The user itself is prompting when an interaction should start, and based on that, also how the interaction should end. And then it's also limited to the way, if we look at the vision aspect to it, we are prompting an image also. It's not continuously watching the situation around it and then deciding when to interact. So that's where the research comes in as to how can we move this towards a more situated, interactive environment. And so some of what we have been demonstrating from a research standpoint came to CVPR last year and is continuing through some of the papers that we are submitting and publishing. So the idea of situated real-time interaction, we look at a domain of fitness coaching, which is an interesting one where the model watches someone exercising and has to, I should say the overall vision language model and system has to decide what kind of feedback to give the user to make sure that they're doing best in their exercise. There might be feedback that is pointed to how they're doing it wrong, and it has to be at the moment in time at which they're doing it wrong, otherwise that feedback is stale and not useful. And the team has done this from an end-to-end fashion in the sense of looking at how we have support for this visual stream, continuing to be updating it, how we interact this. Now we're looking at video, so we have an idea of a 3D CNN and cross attention into the large language model. And then a notion of when to look for the next observation in the video stream or when to respond to the user. And this idea of how to enable that model helps us to build it to be situated real-time interaction. And then to complete this end-to-end is the training of the model. If we look at building an annotated data set so that observations and feedbacks are geared towards improving the user's proficiency in exercising, we find that using these existing models may not be the right way to do it because of the way, for instance, the feedback might be from Video Llama or Video ChatGPT. This is just an observation of what they're seeing. A certain person is standing or wearing, it's not really relevant, like wearing a shirt and shorts, it's not really relevant to helping them exercise. But then with the proper type of annotated feedback to fine-tune this system, we can have things that are, in this particular case, encouraging of them because they're doing the right thing. And in some other examples, it can give them pointers as specifically maybe one leg is not as high or one arm is not aligned. And so that's an idea of how you can go and expand that capability and make it more pointed towards the situation and real time. Associated with this, we did release a benchmark, or sorry, in the process of releasing a benchmark data set to help folks understand how this all comes together. And this is something that shows within these exercises and these clip videos what are some fine-grained question-answer pairs that hope to address how to get a situated real-time agent to properly give feedback through the course of a long-range interaction. And this is an example in fitness coaching, but you can imagine all the different things that can happen with coaching for learning how to cook or learning how to new skill, so forth. And that that takes us on this path that I'll conclude on. That once we have edge, once we have real-time situated, once we have a way of training these systems to be in a full awareness of the environment, then we can start looking at these the robotic interactions. Before, the perception, we can say, is in a kind of a mature state of things. But as we go further, there's a notion of, can we get situated real-time awareness? This is where progress is significantly happening now, thanks to Gen AI. And then a last big piece is, how do we tie this into interaction with the environment? And we have a lot of interaction happening at like a digital kind of space with voice and image and a camera. Now can we do it with physical interaction and controlling actuators on different devices? And so, in conclusion, hopefully you've got a good sense of all the different things that are trending in generative AI and how it really is on a trajectory that makes a lot of sense for us to continue innovating on the edge and bringing it to the edge because of just the ubiquity and the situational awareness of and the different opportunities and the applications of the assistant and the interaction that can happen from this. Hopefully you got a sense of the advancements we're making across a lot of the algorithms, mapping that onto the hardware, onto the software stack. And it's great to see that a lot of what we had in the previous years we are able to build upon them as we go into this new trajectory of personalization, of multimodal, of real-time. And then finally, the idea of having these embodied AI agents as the next big push in generative AI coming to the edge. That sense, hopefully you got a good sense of that, and you're just as excited as our research team is towards exploring where we can go. With that, I'll kind of end and like to thank you all for attending this morning.
Yep. Thank you, Joseph. If you could unshare your presentation so
sure.
Folks can see you, and then looks like we have quite a number of questions here. And maybe I'll just read off some of them and have you provide the answers. Let's start with this. Is it possible to remove unlearned data, such as facial recognition data, in a neural network based on AI system?
Yeah, that's an interesting question. Thank you for the question. From a research standpoint, there are these, it has been a topic even before generative AI, where people do see if there's a way to remove, identify parts of the model that might be associated with certain images, or fine-tune models in such a way that they forget them. Yeah, that is, I would say, like maybe in the space of research right now, a lot of solutions probably are more geared towards coming back to the original data set and filtering it, and then maybe pre-training again with that filtered data.
Okay. Another question is it possible to fine-tune lava then quantize it using the Qualcomm chip?
Yeah, it's certainly possible. That is, depending on what you need to do. That's for our particular example, we quantized the original lava, but we did fine tune our draft components so that it's yeah, it's not it's certainly possible to go and fine tune the original model and then quantize it. And then there are different ways. If your question is about are you fine tuning through LoRa or not, I think either way is possible to go and further quantize the model once you've done fine tuning with those approaches.
Thanks, Joseph. We also had a number of security questions, so maybe I'll just bundle them together and ask you this. How do you enforce security at the edge? And is there a different tool that is monitoring security?
Yeah, thank you for the question. I probably don't have a good answer for you right now, but let me make sure I just I think it's a thoughtful question. I think it's good to bring it up here. There are aspects of security that it's important to understand, like what aspect of security are you curious about, because there's a notion of, are you trying to be robust to like adversarial attack? Is that security angle you're thinking about, or are you trying to keep the model, which is proprietary, you're trying to protect it from other folks, like maybe stealing IP from that model. So those are some angles of security, and yeah, we can see how to address this offline or so. For the purpose of this talk, it's not quite our focus, unfortunately.
Okay. Another question is, could you provide more details about the experimentation platform that you use? So this is hardware, memory size, debugging environment, and are you working with PyTorch or OpenCL?
Yeah, good questions. If I pick some examples, so everything that we do from a demonstration on the phones that I showed through the course of this talk, we leverage the AI stack that Qualcomm commercially provides, and we do, we leverage that as much as we can. Sometimes, because some of these are research demonstrations, we may take, let's say, like proof of concept releases, which are not quite commercialized, but they are largely leveraging what the tools are that are released to our own developers. And the goal is, of course, that we guide the overall commercialization strategy for the tools that eventually go to these users. So so for the different things like Lava, for instance, a lot of those blocks are already commercially available. You can go to AI Hub and you can find a vision transformer. The adapter itself is not a very mundane network that's also supported. And then also the core LLM itself was Llama 2, and that is also should be available on AI Hub. So putting those blocks together, you can get a sense that a lot of those are already available in tools. And so people can essentially try to do these later on. But we'll see. They may be one day released directly on AI Hub, and it can be a lot easier for you to try these things out.
Okay. And then here's another question. Are you seeing much benefit running LLMs like Llama 2 on the phone's GPU or NPU versus the CPU?
Yeah, it's a good question. When we look at the target processor to run, it's probably good to think about also what is the application or the device doing overall. It has been shown through the course of last year that indeed that people can run LLMs on our GPU, they can run them on our NPU, they can run them on our CPU. The SoC itself is quite capable. That said, there is generally a benefit to run things on the NPU, given that CPU is a general purpose processor and may be busy doing other things. And similarly, the GPU itself is used often for rendering too, so it may be busy doing things related to the visual feedback that the AI system might be trying to generate for you. So it comes down to that, and the benefits that we're doing towards, let's say, prompt processing and speculative decoding do fit well, let's say, the high compute capability of the NPU. And that is something that may tilt application development in that direction if you do have like a large initial context that you have to process very quickly. So there are different trade-offs that you might have, and you can assess them and target your core that way.
Okay. Another question is, do you see any specialized models being shipped embedded in mobile apps, or a distribution where there are common models backed into the OS like a common library?
I could say, it's envisioned naturally that this might happen. I can't really say specifically on what commercial offerings might be coming, because sometimes it's for the developer, like the operating system or development framework that's coming. But if you think about some of these things and the rationalization behind them, like a large language model, for instance, does take up some amount of memory, and so it is natural to think about if you want to share that with different applications, it might make sense to have that, let's say, embedded or shared, as you would say in your question, as opposed to having multiple developers try to instantiate multiple models at the same time. And for always on smaller models that are related to the interaction for multimodal, you could make similar argument just by scaling down to the smaller core that needs to be on and power efficient.
Thanks, Joseph. Another question is, are you playing with any tri-state chips?
Sorry, I may not understand what that question means, but
okay.
I can try to look at that offline.
Yep, we could get back to that on this. Another question is, how much advantage does this provide in compute and energy use reduction during training?
What does this refer to?
This is earlier on in the presentation with regards to maybe a slide on training methods that we look at.
Okay. I'm sorry, ask that question one more time. Let me see if I can understand.
How much advantage does this provide in compute and energy use reduction during training?
Okay, well, I'll only guess that this is talking about LoRa. So if there are these techniques known as Q-LoRa as one example, where if you wanted to really reduce the amount of memory used by the training of the model, you can have the base model in a much lower precision, and then have the adapter at a higher precision, and overall that can reduce your amount of memory and generally you can use that different ways. You can train faster on a server, or you could reduce the amount and be able to just train the application on a single GPU. I hope
Okay.
that that's one way to answer it. I hope that it addresses the question.
Thank you. Does Qualcomm have any AI ML for radio performance tuning?
Do we? I mean, that's a broad question. Radio performance tuning. I believe that there has been at previous MWCs some. We have shown that we do like antenna tuning and other things around the. We have a 5G suite, AI suite for our modem releases. So you can generally look at that to see if your deeper question as to what aspect of radio performance tuning you're looking at. But certainly it is an important area that Qualcomm holistically looks at AI to prove various things in our product roadmap, including the modem.
Okay. What are your thoughts on Onyx? Does it ultimately matter how portable models are?
Yeah, it's a bit out of my scope, but thanks for the question. We can try to fill that to some of my colleagues on, for instance, on the AI Hub that might be much better suited to answer that. By the way, that reminds me, there has been Krishna Sridhar of AI Hub team recently had a deep learning AI lecture on running on device, and maybe if you watch that your question might get answered there.
Okay. We have another question from Baman. Nonlinear quantization certainly helps with memory usage. What's the impact to overall computation?
What was the first part of the question again?
Nonlinear quantization certainly helps with memory usage. What's the impact of overall computation?
Yeah, so it's an interesting question. It depends on how you implement some of this. You could, it's not necessarily that we are doing computation in this complicated codebook space. It's more, another way to think about it is also you could represent these weights when you store them and you transfer them, but when you come back to compute, you move to some native format for the compute itself. And you may expand for the purpose of computing efficiently to something like integer again, or FP16. So it's not necessarily, I wouldn't, so if the questioner is wondering if we make compute more complicated because of the different code book, we're not. If they're wondering if we're making the compute more efficient, we're not making compute unique to the code book. So we're leveraging the compute that is available.
Okay, we have time for a few more questions.
Sure. Thank you, everyone, for staying around and asking all these questions.
Yeah, thank you, everyone. Is it possible to embed this technology into existing software, like AI agent software interfaces, and run it on Qualcomm Windows laptops?
And I'm guessing this question is about the orchestration. If so, yeah, it's generally possible to offer this kind of a framework for people to develop upon, or it's possible that it could be embedded so that there's an API that everyone just accesses and uses for their application, further application development on top of it.
Okay. Is fine-tuning preferred more than RAG on edge? If so, why?
Yeah, if it's an interesting way to look at that. I actually think might take a step back from the question and understand what you're trying to do, because even in the space of retrieval, you may not think of it as exclusive to fine tuning. You might even have a retrieval augmented generation, which gets better with fine tuning when you fine tune the embeddings and the generation on the actual database that you're working with. I would think of it like if you're looking to have a model that generalizes well, and you have a bigger model, yeah, that you might rely on putting it together with the database and then trying to address certain things. But that doesn't necessarily mean you want to, if there's a opportunity to have some kind of annotated data set for fine tuning to improve your application, that can still be applied. And then in some cases, it allows you to run with a smaller model, because you can narrow down the domain and take advantage of that.
Okay, last question. Is it possible to do on-device fine-tuning for LLM?
Yeah, great question. That's something that we're actively researching. I mean, it's possible, and then it comes down to like what are the requirements under which you're trying to do things. So last year we did demonstrate that we can do on-device fine-tuning for smaller model for an overall use case that we're improving, let's say like video segmentation, and updating the model essentially in real time for the application as we're trying to use it. Now when we look towards dealing with a much bigger model, we see, okay, can we take advantage of LoRa in a certain way, such that we reduce the amount of trainable parameters that we have, or the overall resident memory that we need for that. And then on top of that, are there further optimizations we can do towards what architecture or what overall application flow are we targeting, to update. In your particular question, you want an LLM to be fine-tuned to a certain use case. Is that use case style transfer, or is it adapting to a different domain? So some of these become very task specific, and that's where we're looking at different tasks. And we're not just looking at LLM, we're also looking at fine-tuning for these generative image use cases too. But I would say, yeah, things are possible. It's just a matter of what's the best way to do it from our perspective.
Okay, thank you, Joseph. Unfortunately, we won't be able to get through all of the questions, but we really appreciate your time, and hopefully all of you found this webinar to be extremely helpful and valuable. Thank you, Joseph, once again, and thank you everyone for joining.
Yeah, thank you again, everyone, for joining.